Hey everybody, this is Luke Tomasello, author of the Munge Adaptive Cryptography System. In this first video, I just wanted to give you a brief overview of the different components, how they fit together, and how you might use them in your own app or deployment. There's two main parts here. There's the library itself and the workbench. And we will spend more time on the workbench, but I did want to touch on the library. As you can see, this is a minimal app that uses the Munge cryptographic library. And as you can see, I mean, it's not unlike most other cryptography systems. You create an object with a password and a salt, and then you will later use this object to both encrypt and decrypt content. There's very low friction in using the library, and it's available today on my GitHub and can be dropped into your app or your deployment right away. And it comes stock with out of the box. It has a number of built-in profiles for different types of input content, and that's really what we'll be talking about today. You can see it here. The one thing that makes adaptive cryptography different is that adaptive cryptography executes different algorithms for an input data type. So for instance, if you are encrypting human readable text, it will select one type of encryption algorithm. If you're encrypting executable files or highly binary files or highly random data, high entropy data, then it will select a different algorithm. And the reason for this is that adaptive cryptography wants to do the least amount of work for the best outcome. And the best outcome is measured by a number of metrics that measure the cryptographic strength. So for instance, entropy and key-dependency, bit variance, all of these things. We measure, our harness will, our workbench will measure 9 different metrics, and you'll be able to see how Munge stacks up against AES. I use AES just because it's a standard and people are very familiar with it, so that's what we compare against. But sort of recap here, you encrypt and decrypt just like you always would, and you ask the system for an input profile, or you can actually hand code them. It's a very simple structure, but we give you a tool to get to select the best input profile for whatever the input data is. Okay, so let's hop over to the workbench and see what the workbench is useful for. And it's actually the tool which I use to build profiles. Okay, so let's take a look at the workbench here. All right, so here is our workbench. What you're seeing here is that we have 50 transforms. So what a profile is a sequence of these transforms. The ones in yellow on the right here are inverse transforms, and the ones on the left are forward transforms, or transforms which are self-inverting, like XOR up here, number 1. It doesn't have an inverse because it is its own inverse. So we have all of these transforms to work with. So a sequence is some number of transforms in a particular order, and the transforms each have their own rounds. So if you had 4 transforms, each of them could have their own rounds count. You might execute the first one 2 times, the next one 3 times, the next one 1 time, whatever. And then there is a global rounds which executes the entire sequence that number of times. So you can, the Workbench is kind of fun. You can play with the different transforms to see what type of, how well it works, and you can use it to discover new sequences. And without diving too deeply into the math, there are literally, if you're looking at maybe 5 transforms, you've got literally trillions of combinations of algorithms here. When you consider each of the transforms has up to 255 rounds, and then the global rounds is also 255, plus you've got, you know, we'll just say 30 transforms, just the forward transforms. You've got trillions of combinations. So that's how we zero in on particular data types, right? So your high entropy data is going to have a sequence that is comprised of 3, 4, 5 of these transforms, and natural text is going to be a completely different set, and they're going to be highly tuned and overfit for that data. And we can talk about the overfitting and our scoring model and why it's not a bad thing. Okay, so let's just try one here. Let's add a transform. We don't have any transforms selected. Let's add XOR here just for fun. Okay, so we've added the XOR transform. So let's run the sequence. Okay, so as you can see up here at the top, it's telling us that the currently selected data type is random, and there is 1 global round. The Workbench has several built-in data types. They're blocks of 4K of random data, natural data, which is human readable text, sequence data, and then combined data, which is a combination of all 3. Okay, so let's switch it over to combined data. Okay, so as you can see, we've got combined data, and it's actually listing the other configuration parameters here. When you set a parameter, it will list whatever the current parameters are. So you can see that our input type here is indeed combined. Nothing else here is too important for us, except we are using a practical scoring model. We'll talk about that more in follow-on videos. But that's actually all we really need for now. So let's run this sequence, okay, and see what happens. So we're going to be feeding the XOR transform combined data, and then we're going to score it and see how we did. Okay. All right. So what do we got here? Well, one of the things it does is give you a visualization of the data up here, and you can look at the raw input data, and then it'll show you what bits changed in the encrypted data, the comparison between the bits, and then the decrypted data here. Okay, a little bit of a header here, and it's telling us that entropy failed. We're shooting for 7.95. We got 7.94, so that's a fail. Bit variance fail. Sliding window passed. And the red metrics here are the most important for cryptography. there are other modes. There is, right now we are operating in cryptographic mode, so the metrics are weighted by importance for cryptography. You can set that mode to exploratory, where it's just a flat reading of all of the different metrics. Okay, so you can see here that we didn't do well. We only passed 6 of 9 metrics. Reversibility, you're always going to see a pass. All of the transforms are always reversible. Our aggregate score here is not too great. So that's it. That's sort of the model. All right, so let's go back to our sequence. So one of the cool things here is that you can now add other transforms to the sequence, as many as you want, in any order. Duplicates are allowed. So let's go ahead and add let's add this guy, 49. Additive scatter forward transform. So we just say 49. And now, as you can see, we have our XOR, which receives the plain text. It does its XOR transform, and then it pipes it into additive scatter forward transform. Okay, so let's just take a look and see what that looks like. All right, so we passed entropy. Okay, so we're doing a little bit better. We went from 70s to 82, so we actually moved up quite a lot. It's actually not too bad, but it's certainly not the grade that we want. So let's take a quick look and see what this means here again. I'm going to pick. Well, let me back up. So, since there are trillions of possible combinations here, and we haven't even started changing the transform rounds, we're just running with a global rounds of 1. It's impossible for a human to enumerate all of the different sequences and possibilities. So we have a function here. I might be able to demonstrate it here, called Munge. And what Munge does is you set the data type, so for instance, natural data or combined data, how many metrics need to pass. I usually say 7 of the 9, and then let Munge run. And if you're running, 5 transforms, that could take a week. This machine is pretty powerful, and it can still take a week. If you're running 4 transforms, we're talking, maybe 4 hours or so. So it's a very intensive. It's a multi-threaded app, uses the entire capacity of the machine, but it's very intensive. But it can visit many millions of configurations, and derive the best configurations for the given data type that meet the requirements. For instance, passing 7 of 9 transforms. Okay, so let's look at the output of a Munge. So here are is the analysis summary of a Munge for combined data, practical scoring, and the max sequence length here is 4. And as I mentioned, this take an hour, a couple hours, depending on your machine. So this is the number 1 contender. This is the contender that did the best. We actually currently have it set up to record the top 1,000. This opens the door to somebody interested in machine learning can probably learn from this file what transforms in what order and round configurations would perform optimally. But this particular sequence is contender 1, and the sequence is this one right here. So we're going to go ahead and paste that into the Workbench just so we can play with it here in real time. Like I said, though, discovering this sequence manually is not impossible, but highly unlikely. So let's go ahead. You just enter a $sign, and then you can paste in a sequence, and there you have it. Now we have our sequence. Let's take a quick look and see what that actually is doing. So that sequence is really saying that we're going to take the incoming plain text, pipe it through chunked feedback transform. That goes into a cascade of 3 substitution tables, sliding mask overlay, bit flip butterfly, and then the ciphertext is the output. So that's what we're going to be executing here. All right, so let's run it. All right, so here you'll see that we got a pretty good aggregate score. And in later videos, I'll talk about the scoring system. But this is actually pretty good. And as you can see, it passed 9 of 9 metrics. So it got a passing score on every metric here. And it did that. It was able to complete that in 1.1 milliseconds. So that's good. But how good is it actually? So I've included AES in the Workbench so that we can measure it against sort of a known quantity. The one thing to note here, though, is that I'm using a CLR version of AES, just like Munge here is a CLR, Common Language Runtime, so that we're measuring apples to apples. In an earlier version of the Workbench, I was measuring it against the native AES, and my particular computer has, silicon support, in the chips for AES. And so while I could beat it metrics-wise, I could never approach it speed-wise. So in this demonstration here, it's apples to apples. I'm running AES in software. So let's run it. Okay, so we're going to run a command, run comparative analysis. All right, so this is where we run our sequence with this input data against both Munge and AES. All right. So let's see, what can we see right here? You can see that Munge only took 103 milliseconds, and AES took 204 milliseconds. So Munge is significantly faster. You'll also notice that AES's aggregate score is 74.6, and they passed 7 of 9 metrics. If we go up here to Munge, you'll see that Munge had a significantly higher aggregate score and passed all 9 of 9 metrics. I think I have a side-by-side here, which is a little bit easier to look at. So here they all are stacked up. I don't want to go through each and every one, but you can see that this is actually this is actually for random data, so it's not a good test. We actually failed entropy here. Yeah, this is the wrong graphic, but we can see what we wanted to see in this linear table. We're running against combined data. All right, so that's how we stack up against AES into head-to-head matchups. Okay, so we have a transform here. We have a sequence of transforms, and so there's a couple of tools. I already touched on Munge, how we arrive at these optimal transforms, but the truth is they're actually not quite optimal, because Munge doesn't visit every global round configuration or every transform round configuration. So we have a separate tool for that. So as you can see, so let's look a little bit closer here. When Munge runs, it only runs transform rounds of 1. So all of these are transform rounds of 1. All right. And I happen to know through some heuristic analysis that global rounds of 6 is about right for combined data. That's where all of the sequences do pretty good. 6 rounds beats all of the other rounds. But let's now fine-tune this sequence and see if we can squeeze out a little bit better performance. By increasing rounds, we may in fact incur some speed, increasing the speed or decreasing the speed, depending if we're decreasing the global rounds or increasing the transform rounds. But it really is measuring the metric performance to see if we can get even a higher score. Okay, so the way that this is done is we optimize sequence. All right, so we're going to optimize sequence. I think it's max 1. No, starting. So what I'm saying here is optimize the global rounds and the transform rounds, and it will max out at 9. You can actually override that and go much higher, up to 255, but I've found that 9 usually does reasonably well. But we're going to start at global round 1, so we're going to ignore our suggested global rounds of 6. We're going to start at global rounds 1 and then find every combination of the transform rounds up to rounds 9, and to see if we can get a higher score than this current configuration. All right, let's go. All right, so it's just asking now if we want to continue. If you have, obviously, the more, this is my development machine, 4 cores. It's okay. My beast machine has 20 cores, and so this runs much quicker over there. We're going to proceed. Yes. All right. Now, as you can see, it's already improving. Let's see if I can grow this a little bit. Yeah. So it's already improving, and it's going to run for a while. I'll pause the video here and resume it once it finishes. But we started out with 92, 37, 60, and we're already up to that here with the last one that was discovered was that same score. And as you can see, it actually matches. one transform round for each and global rounds of 6 actually turned out to be the best so far. So I'll pause it here. We'll come back and see if we don't get any improvement. Okay, so as you can see, our optimizer found a better sequence than the default one discovered by Munge. And what it did here was it increased the chunked feedback to 4 transform rounds. It left cascade at 1, and sliding mask overlay, it increased it to 4 transform rounds. And then finally, it decreased the global rounds to 2 instead of 6. And we have a slightly better score. And we're now being asked, do we wish to make this the current sequence? Let's do that. So yes. Okay, so let's grab this, and we're going to paste it in, make that our current sequence. All right, so this is our newly discovered sequence, and if we wanted to save it as a reusable profile, we could just save profile and give it a name. We'll call it foo. Okay, foo is saved. Okay, now let's take a look at the profile we just saved. Okay, so here is our profile that we just created. It tells us that we have, this is the ID of this transform, this many transform rounds, and so on, and a global rounds of 2. And this is actually aggregate score. It's not really used by the encryption. Neither is the name, actually. These were useful for the profile manager, so you can call them up by name or compare them to other profiles. But so this is what they look like. And you could, if you weren't interested in dynamically loading different profiles, you can actually hard code these structures into your application. If you were, say, always processing textual data, maybe you just hard code this in there and you can skip the whole process of loading a profile. You just pass this directly to the encryptor. Okay, so I think we've pretty much covered the things I wanted to cover. Let's though do the one last piece of this puzzle. Okay, so we're currently configured with combined data. That's fine. We're going to go ahead and run a Munge now. So if you remember, Munge is how we find the best sequences given one transform round and some number of global rounds. Okay, so we're going to go ahead and run it, but we're going to do a rather simple sequence of length 3, and this will take a short while. What I'll do is I'll get us started, then I'll pause it, and then I will resume the video after the Munge has completed, and we can look at our results. All right, so let's do that. Okay, so Munge is now running. It already created level 1, which is not interesting, just 1 transform per sequence. Now it's processing 2 transforms, Then it will do 3, and then we'll resume the video and see what we got. And we're back. So our level 3 Munge completed for combined data. And let's go take a look at the output folder for the Workbench. And see what we got. So I've sorted it by date, and as you can see, we have a new contender file for level 3 for combined data, and a couple other configuration parameters. So let's see what we got here. Okay, so for 3 transforms, this one did pretty well. We're into the 92s. 92.37.6 is good. We got 9 of 9. We passed 9 of 9. So likely this one is going to clobber AES as well. And if we optimize it, we'll likely get a better score as well. So that's the model for munging. I'm going to go ahead and paste this in here. We're going to use it in the Workbench. $, and then you just paste. All right, and now let's run it against AES. And yeah, as you can see, we did really well here. We got a good score, 9 of 9. We roughly half the, or double the speed of AES. So that's the model. You will define how many transforms you want in your sequence. What I have found is that 5 transforms is pretty much optimal, although it's pretty expensive to run, maybe a week on a standard PC. But when you're done, you'll have 1,000 contenders, and that first one is going to be about as good as it gets until you optimize it, and then you'll really have a god sequence. Okay, so let's for fun, we'll save that as foo, and we'll overwrite the old one. All right, we're being asked to overwrite it, yes. And now let's delete it. Don't really want it. Okay, so that's sort of the profile management. You'll run Munge on the data type you want, and you'll specify the number of transforms you're going to allow in the sequence. Like we did here, 3 transforms runs pretty quick, 4 a couple hours, and 5 we get into like the week time frame, 1 week time frame. And if you go to 6, you're out there to, like, you know, at least on my machine, I don't know, 70 days or something. It's quite a lot. So let's take a quick look at a transform. I'm sorry, not a transform, at a profile. So you can get kind of an idea. This is from my LinkedIn post. So what we have here on the left side is a transform for combined data, and it's telling us here that we're using the butterfly transform, substitution bytes, another butterfly with rotation, another substitute with XOR, and then a butterfly with rotation, and global round 6. And they're all transform rounds 1, except for this guy. The first butterfly gets 3 rounds. And if you look over here on the right, this is just a pseudocode explanation of how this profile is interpreted by the encryption engine. So your global rounds here on the left define the outermost loop, how many times this entire sequence will be executed, and then in order for each transform, you're going to execute that number of rounds on that transform. Okay, so I think that's really all I wanted to cover today. I'll do some deep dives on other topics if there's anything I went over too quickly, or areas of the workbench or the library that you would like a little bit more detail on. I'm happy to do it. One final thought I would leave you with is that we have baked into the workbench, four of the probably the most common data types. Most files, PDFs, binaries, images fall into one of the canned types. However, if you have something very specific like telemetry data, for instance, you can ask the workbench to load the telemetry data and then create sequences that are optimized for that particular data type. So for instance, you would load your telemetry.bin or telemetry.txt, whatever it is, and then you would go ahead and you would run a Munge on it, 3, 4, 5 sequence transforms. Then you'd optimize it, you'd save your profile, and then you use that profile when you're encrypting. All right, so I think that's it. Leave a comment if you would like to expand on anything that I've covered here, or you would like to look at other capabilities of the workbench, or you would like more specific example usage of the library itself. All right, thanks. Bye.